Recording in progress.
All right, let's get started. So hi, everyone. I'm Dennis. I'm going to talk about the full stack GPU training and an architecture of RL policy with optimization-based control. Okay, so the first part is about the reinforcement learning training part. The biggest limitation for reinforcement learning is it's slow. It's can take days, even months to train a policy. And most of the time, just like the waiting to get some result. If it doesn't work, then you basically redo all of the work. It's a pretty tedious work. And most of the time, the training spend is on CPU for the simulation step. That takes most of the time. Even you spend sometimes for the reduce the time and then run GPU for the simulation. The data transfer between GPU and the CPU can be the bottleneck. And so we in NVIDIA created a solution that we can enable everything run on GPU. We can have a simulation, compute reward and observation, and do the forward passing everything on GPU. And this is a much faster and a much efficient way to train reinforcement learning. For our use case, like the quadruped locomotion, we can reduce the training time from days to minutes. Like you can, because the GPU, we can easily massive parallelize and the simulation. We can simulate the entire robot army in a fraction of time, which will cost to simulate on the CPU. So that's a benefit for this GPU training. And what can we do given this powerful GPU training? What kind of the setups that we can do to improve the performance? Here I set up this reinforcement learning plus model-based control framework, where the reinforcement learning is for a high-level planner that it takes the input from the robots, like the IMU states, joint state, and the local high map. And it can output central mass target, context sequence, fit target position to a low-level controller. A low-level model-based controller solves a QP for inverse dynamics, converts the ground reaction force to motor, do all sorts of the low-level work. And for this setup, it's benefits in both the RL and the QP side, because the RL, it can predict the long horizon, and it can get the return. To predict the future, it can make the discrete decision, and they can have other benefit. And the QP, it can have the high bandwidth. It can like run on 500 hertz, because they don't have to do any MPC or consider the horizon. It can run very fast, and they can take care of the friction constraint directly, and in the friction cone in the QP, and they can do whole body control by mix of different targets or different output. So we have the three kind of outputs from this RL planner, but we're not necessarily learn all of them. In fact, we can learn a fraction of them, or we can learn none of them, or we can learn all of them. So this is a planner comparison for like why we do want to make all of them be a nerd policy instead of using some simple heuristics to make the plan. First of all, I'm gonna show you this planner, just all by heuristic. And we set up the test is the like I go walk on this continuous with a slight up and down slope um, environment where like a girl can see this local map with this red grid. It uses a reverse heuristic to do the full placement. And then you use this local height maps to change this context height, and they can adaptive the pitch angle and the body height based on the terrain. So it's a pretty good controller in a sense for this continuous ground. It can reject a good amount of the perturbation, the walk um, pretty stable and can track the different target velocity. So it's a strong baseline. But when we discretize the ground, say we keep this terrain profile, but just change the continuous ground to stepping stone, it has some problem. Because reverse heuristic doesn't work that well. Even I make it trying to avoid the gap. But because the full location was restricted, and it doesn't coordinate with the center mass planning very well, so that doesn't work on this case. And what about we learn center mass position, so that in this case the center mass acceleration was commanded by this learning policy. So it know how to collaborate with the center mass position with the foot's contact position, and it supposed to move the center mass or, close to the line of this two contact foot. That way actually works with much less like lateral velocity, and actually can complete this task with forward walking. So it's all good. What's a problem for this controller? Why do we need to learn the rest of them? Here's a problem. If we just send high speed, like everything looks reasonable, but if we just let it stay here, like send the target speed to 0, or make a very slow speed, like the 0.1 meter per second, it doesn't look natural. The legs keep moving like with a constant frequency, and it's always like do this step in place with a very slow motion. It just wastes energy, where it doesn't have to do this. Like you expect it just like a standing, or just like move the leg very slowly. So that's a problem. It's more of a stylish and the energy consumption problem instead of a stability problem. Well, stability, I am sure like this will be have some stability as well. So let's see. What about the policy 2? We learn center mass acceleration and the contact sequence together. Here we go. So the obvious difference now it can stand when speed is 0, and when speed is 0.5, you can walk. Then like I said, command to stop, then it actually stop. You just stand there, not move at all, and I can shift, send a different command. The interesting part now, if I send a slow speed, like 0.1, it will just shift the mass forward, then move the leg. It will shift first, not constantly stepping. It will stepping for 1 or 2 and just stop. This is much more reasonable gait. You think like you can do a complete stop, or you can move fast, or you can do slow. This is more nature and reasonable gaits in my opinion. That's why we need to know the contact sequence instead of to do a fixed one all the time. One thing to mention is this trotting gait is purely NER. Even we don't fix the gaits, all the gaits are treated independently. Just for our reward function, it's prefer either trot or stance, but actually it can do any kind of gait if you want. To prove that, say if you have a wide gap, you're probably not going to trot across it. You probably want to try to do the bounding gaits. That's a motivation. We change the environment. And let's see, if we have a large gap, given the same rewards, same part, like output and inputs in the policy, it change the context sequence. You will prefer this like galloping gaze to across this large gap because you find like trotting is hard to do it. So it's changed the gait. Eventually, we're working on trying to let us say on the flat ground, it will do trotting or walking, but once you see a large gap, it will automatically switch to this bounding, this galloping gait, or if we do have a skateboarding, it will just move one side of the leg, something automatically switch it. We're still working the progress of train all of them, but I expect that will be the best policy given the trend like the more learning replace the heuristics is better. All right, that's all. Thank you. Yeah, happy to take any question.